Okay, welcome to the Computer Science and Engineering Colloquium. It's great today to have Amit Sahai here to talk to us about a portion of his PhD work on statistical zero knowledge. Amit was an undergrad at UC Berkeley, where he won the Computing Research Association Best Undergraduate Award, the national award, which is a pretty high honor already. So, and has been working at MIT on his PhD with Shafi Goldwasser, and he's going to talk to us about his work. Thanks.
Okay. Well, thank you very much for the introduction. And I'd like to encourage any questions you might have about the work that I'm presenting. Please feel free to ask during my talk. So again, I'll be talking about statistical zero knowledge. Zero knowledge proofs are fascinating constructs in which one party, called the prover, convinces another party, called the verifier, that some assertion is true. And yet, the verifier learns nothing beyond the validity of the assertion being proven. In this talk, we'll focus on a type of zero knowledge called statistical zero knowledge, where we take this critical condition that the verifier learns nothing and interpret it in a strong information-theoretic sense. So let's begin with an example. Suppose I had two graphs, G0 and G1. Now, a natural question to ask about such a pair of graphs is whether these two graphs are really the same graph under some isomorphism. In other words, if there's just one graph and only the names of the vertices have been changed. For example, here we see that the answer is yes. And if we follow the relabeling given here, we see that it does indeed map G0 to G1, preserving the structure of the graph. So if I wanted to convince you that these two graphs are isomorphic, one way I could do so would be to simply reveal this isomorphism to you. And you could check for yourself that it does indeed map G0 to G1. But in fact, it's possible for me to convince you that these two graphs are isomorphic without revealing anything about what the isomorphism is. And here's how we do it. So in the protocol, the prover in the first step will take the first graph, G0, and choose a random permutation on the vertex labels and apply it to this graph, G0, to produce a new graph, H, which it will send over to the verifier. The verifier will take this graph H, this randomly relabeled copy of G0, and store it aside, and then issue a random challenge to the prover. The verifier will choose either G0 or G1 at random by flipping a coin, and then challenge the prover to respond with a relabeling that maps the verifier's chosen graph to the graph H sent in the first message. If the prover is able to produce such a relabeling, then the verifier accepts the proof. Otherwise, she rejects the proof. Now, the first question to ask about this protocol is, why is it convincing? Why should the verifier really become convinced that these two graphs really are isomorphic? So to see why that's the case, suppose not. Suppose that, in fact, the prover was lying and the two graphs were not isomorphic to each other. Well, in that case, no matter what graph H the prover sends in the first message, it can only be isomorphic to one of the two graphs, either G0 or G1, but not both, since they're not isomorphic to each other. And therefore, if the verifier challenges the prover with the graph that H is not isomorphic to, the prover will simply be unable to produce a relabeling mapping the verifier's chosen graph to the graph H. And so we see that with probability of at least 1/2, the verifier will catch the prover in its lie. And in particular, if we repeat this protocol k times, then the probability that the prover will be able to convince the verifier in each of the k protocols becomes exponentially small. So the verifier can gain an arbitrary level of confidence that these two graphs really are isomorphic by going through this protocol many different times. So in this sense, we say this protocol is convincing. Now, what about zero knowledge? In what sense can we say that the verifier doesn't learn anything in this protocol? Well, the intuition that we'll try to achieve is the following. We'll show that anything that the verifier does learn in this protocol from the prover, she in fact could have learned completely on her own, without having any help from the prover and without having any special information whatsoever. And if this is the case, when we say this protocol is zero knowledge, again, since all that she learned, she could have learned on her own anyway. Now, what does the verifier obtain in this protocol? At the end of the protocol, we can capture all of our information by the transcript of our interaction with the prover. And what we'll show is that, in fact, the verifier can generate such a transcript of our interaction with the prover completely on her own, without having any help from the prover and without having any special information whatsoever. The way that she'll do so is by first choosing one of the two graphs, either G0 or G1 at random, by flipping a coin. She'll then choose a random relabeling of the vertices pi and let H be this relabeling pi applied to her chosen graph, and then use these three elements to produce a transcript of the protocol. And what we can show is that, in fact, the distribution of transcripts produced in this manner by the verifier completely on her own is, in fact, identical to the distribution of transcripts she would have seen in an actual execution of the protocol. And therefore, since all the information that the verifier obtains in the protocol she could have generated completely on her own, we say that this protocol is zero knowledge. So at this point, I'd like to stop and take any questions that anyone might have about this protocol or about the intuition behind zero knowledge. Okay, so great. In that case, I'll move on. So I've given you one example of a protocol for the problem of graph isomorphism, which is a problem that we know is hard in general. But in fact, it's not the only example that we have. There are several other problems that we believe to be hard, and in fact are useful cryptographically, that end up admitting statistical zero-knowledge proofs. For example, the problem of quadratic residuosity or quadratic non-residuosity, the problems of graph isomorphism, as we saw, along with the problem of graph non-isomorphism, a problem equivalent to the discrete logarithm problem, along with approximate versions of the shortest and closest vector problems in a lattice. All of these problems are problems that we believe to be hard and yet have statistical zero-knowledge proofs. But on the other hand, it is also known that if a problem has a statistical zero-knowledge proof, then it can't be NP-hard, unless an analog of the P equals NP result holds. So we have that statistical zero-knowledge, on the one hand, contains problems that we believe to be hard, and yet on the other hand, it can't contain NP-hard problems. So it occupies an intriguing position in complexity theory, somewhere between the tractable problems in P and the extremely difficult problems that are NP-hard. This gives us a strong motivation from a complexity-theoretic perspective to study statistical zero-knowledge in greater detail. Statistical zero-knowledge is also very well motivated from a cryptographic point of view. Zero-knowledge protocols in general have vast applicability throughout cryptography and are especially useful in constructing secure cryptographic protocols. And of all the different kinds of zero-knowledge protocols, statistical zero-knowledge proofs, the kind that we consider in this talk, essentially have the strongest security guarantee of all the different kinds of zero-knowledge protocols. And therefore, whenever we can use statistical zero-knowledge proofs in cryptographic protocols, those protocols inherit the strong security properties of statistical zero-knowledge proofs. This is, for example, the case with identification schemes. But statistical zero-knowledge proofs are perhaps even more strongly motivated from a more theoretical perspective. And this is because we're often able to prove security results about statistical zero-knowledge without making any unproven assumptions. This is in stark contrast to almost all the rest of cryptography, where we typically need very strong unproven assumptions. For example, the assumption that factoring large numbers is difficult. And when we're able to prove such security results without making any unproven assumptions, not only do we place our security on a more firm foundation, but we also gain greater insight into where security comes from mathematically within cryptographic protocols. Another interesting thing about statistical zero-knowledge is that we're often able to generalize results about statistical zero-knowledge to other types of zero-knowledge as well. So research on statistical zero-knowledge has often unexpected payoffs in giving us information about other more general classes as well. These motivations have led a number of researchers to study statistical zero-knowledge over the years. And if we take a look at how the field has developed over the last 15 years, we find that after the initial pioneering work of Goldwasser, Micali, and Rackoff introducing zero-knowledge proofs, research on statistical zero-knowledge has generally proceeded along one of several distinct research threads, each looking at statistical zero-knowledge from a slightly different point of view and using surprisingly few techniques in common between them. As a result, over the years, we've seen a number of very interesting and important results about statistical zero knowledge. And yet, our view of statistical zero knowledge has remained fragmented. And indeed, in almost all of these areas, there are many fundamental questions about statistical zero knowledge that have remained open over the years. Our goal, then, in this talk, will be to seek a unified, simpler, and deeper understanding of statistical zero knowledge. One that will not only allow us to unify the previous work in the area, but also allow us to answer many of the fundamental questions that have remained open over the years. We accomplish this goal through two primary results. In our first result, we give a complete problem for the class of all assertions that admit statistical zero knowledge proofs. And in the second result, we show how to we give a transformation that fortifies statistical zero knowledge proofs against abuse by cheating verifiers. So let's talk about these results in greater detail. In the first result, we give a complete problem for statistical zero knowledge. This is in the same sense as the theory of NP completeness. So we give a single problem that characterizes all of statistical zero knowledge in a new way. This characterization allows us to simplify and unify the study of the entire class of statistical zero knowledge. And our problem has several immediate applications. We're able to, in particular, show that all statistical zero knowledge proofs can be transformed into a particularly simple canonical form, which we'll talk about more later on. We also show, again, as I mentioned earlier, how to simplify the proofs of nearly all known previous results in the area. And we're not just limited to proving results that were already known. We're also able to establish many interesting new results, and one result that I'll highlight in the talk is a result that shows how to build statistical zero knowledge proofs for much more complex assertions than were previously known. In the second result, we show how to fortify statistical zero knowledge proofs against abuse by cheating verifiers. These are verifiers that deviate from the protocol in an effort to extract information from the prover. And in particular, we show how to transform any proof that is zero knowledge only for the honest verifier. That is a verifier that just follows the protocol as specified, into one that is zero knowledge for any verifier, no matter how it deviates from the protocol in an effort to extract information from the prover. Furthermore, this security result requires no unproven assumptions and also extends to other types of zero knowledge as well. The work that I'll be presenting in this talk is based on a series of joint papers with Oded Goldreich and Cyril Vadan. Now, before I go on into the discussion of these results, I'd first like to start with some definitions, some basic definitions. So we'll be taking the standard notion in computer science of decision problems and generalizing them slightly to what are called promise problems. So typically in computer science, we think of decision problems as being languages, where all inputs are either yes instances or no instances. For example, a Boolean formula is either satisfiable or unsatisfiable. In a promise problem, we again have some inputs that are yes instances, some inputs that are no instances, but we also have several other inputs that are simply excluded. They're promised not to occur as inputs to our problem. So an example of a promise problem would be the unique satisfiability problem. Here, instances are again Boolean formulas, where yes instances are formulas that have exactly one satisfying assignment, no instances are formulas that have no satisfying assignments, and all formulas that have two or more satisfying assignments are simply excluded. They're promised not to occur as inputs to our problem. So with this definition, we'll begin our definition of a statistical zero knowledge proof for our promise problem pi. So a statistical zero knowledge proof is an interactive protocol in which a computationally unbounded prover talks back and forth with a probabilistic polynomial time verifier in an effort to convince it that some input string x is a yes instance of a promise problem pi. And we have two basic conditions that we require that enforce the notion of a convincing proof. So here are two basic conditions that, first of all, when x is a yes instance, in other words, when the prover is telling the truth, when it's really trying to convince the verifier of a true assertion, in that case, if the prover follows the protocol as specified, then the verifier should accept with high probability. On the other hand, if x is a no instance, if the prover is lying, in that case, the verifier should reject with high probability no matter what strategy the prover uses. So no matter how the prover tries to convince the verifier, he should generally always fail. So that's our notion of a convincing proof. Now, to get our notion of zero knowledge, we'll take the intuition that we had from our example in graph isomorphism and turn that into our formal definition. So again, our intuition was that when the assertion being proven was true, in that case, the verifier should be able to simulate her view of the interaction with the prover completely on her own, without having any help from the prover at all, and without having any special information whatsoever. And again, because she can simulate her view completely on her own, she must not learn anything that she couldn't have learned on her own anyway. And we take this intuition and make it formal by requiring that there exists a probabilistic polynomial time simulator such that when given as an input a yes instance to the problem, the output distribution of the simulator is actually statistically almost identical to the distribution of the verifier's view of the interaction with the prover in real life. In other words, if we think of two boxes, in one box we have the real prover and the real verifier talking back and forth, and they produce some transcript, and in the other box we just have the simulator, then these two boxes, as viewed as distributions, should be statistically almost identical to each other. And with this definition, we can define a proof system that satisfies this definition to be a statistical zero-knowledge proof. So one thing I'd like to point out is that the definition that I've given you here assumes what we call an honest verifier. This is because we only require the simulator to be able to simulate the interaction of an honest verifier, a verifier that follows the protocol, together with the prover. We'll see what happens with cheating verifiers later on in the talk. And so given this definition, we can define the complexity class, SCK, to consist of all promise problems that admit statistical zero-knowledge proofs. Yes?
What do you mean by statistically almost identical?
So in this case, what we mean is that even an unboundedly powerful adversary, if given a sample from one of these two distributions, would have only an exponentially small chance, exponentially small advantage in distinguishing which one it came from. That's one way of seeing this notion. I'll also give you a more formal notion of distance that we'll talk about later on.
So exponential in the size of the sample.
Right. In the sense that the probability of distinguishing is exponentially close to each other. So just to make this more concrete, if we recall back again to our example protocol for graph isomorphism, where again in the first step, the prover chooses a randomly labeled copy of G0, then the verifier flips a coin, and the prover must respond with a relabeling mapping the verifier's chosen graph to H. We can see formally that indeed this protocol is simulable. It has a simulator satisfying this definition. So if we recall, the simulator that we were considering earlier first chose either G0 or G1 by flipping a coin, then chose a random relabeling pi, and finally let H equal pi applied to this random graph. So we can think of the distribution produced by the protocol and produced by the simulator in these two boxes. And if we see, the only difference between these two distributions is that for the protocol, H is always a random relabeling of G0, whereas for the simulator, H is a random relabeling of either G0 or G1. But now, if the two graphs really are isomorphic to each other, in that case, a random relabeling of G0 is also a random relabeling of G1. And indeed, these two distributions are identically distributed. And therefore, the simulator distribution and the protocol distribution will in fact be identically distributed. And that's why it really is a statistical zero-knowledge proof for graph isomorphism. So we can now move on to the first result, which is a complete problem for statistical zero-knowledge. So again, most of us, when we hear the word complete problem, we think of the theory of NP-completeness, where, for example, we know that the satisfiability problem is NP-complete because, first of all problems in NP reduce the satisfiability. In other words, for any problem in NP, there's a polynomial time transformation that transforms instances of that problem to instances of satisfiability. And on the other hand, we also have the satisfiability itself is in NP. And these two conditions together tell us that indeed satisfiability is complete for NP. Now, most of us, when we hear that our problem is NP complete, we immediately have a negative reaction. We think, this problem must be really hard. But in fact, there's also a more positive way of looking at NP completeness. And that is the fact that if a problem is NP complete, that means a single problem characterizes all of NP. And therefore, in particular, any questions that we might have about NP altogether as a class can be essentially reduced to questions about a single complete problem. Our goal in this talk will be to accomplish the same situation, to create the same situation for statistical zero knowledge, to find a single problem that is actually complete for all of statistical zero knowledge. Which will again allow us to reduce questions now about all of statistical zero knowledge to questions just about a single complete problem. The story of the study of the complexity of statistical zero knowledge actually has a long history. And we find that, as I mentioned earlier, most of the initial work studying statistical zero knowledge from a complexity-theoretic perspective concentrated on trying to find certain specific problems that have statistical zero knowledge proofs. And indeed, many problems that we believe to be hard were shown to have statistical zero knowledge proofs. The first researcher who tried to argue about all of statistical zero knowledge altogether was Fortnow. And what he tried to show was an interesting counterpoint to what was already known. He tried to argue that, in fact, if a problem has a statistical zero knowledge proof, then it can't be too hard. And in particular, the work that he started eventually led to a proof that, indeed, statistical zero knowledge can't contain NP hard problems unless an analog of the P equals NP result holds. So through his work, Fortnow was able to obtain an upper bound on the complexity of statistical zero knowledge. He's able to show that all statistical zero knowledge can't be too hard. But he wasn't able to obtain a characterization of statistical zero knowledge, which is what we're after. Now, before I can tell you what our characterization is, I first have to define a few specific notions, which will also clarify the earlier question about how we compare distributions. So first, we'll define the notion of statistical difference, which is a metric between probability distributions. So given two distributions x and y, we define the statistical difference between them in the following manner. If we consider the probability mass functions of the two distributions, then the statistical difference between them is simply the sum of the differences between each of the probabilities divided by 2. So we see that if the statistical difference between two distributions, for example, is 0, that means two distributions must be exactly identical to each other. On the other hand, if the statistical difference is 1, that means the two distributions are actually completely disjoint from each other. So that's our notion of distance between two distributions. We'll also define a notion of a sampleable distribution, where we'll associate with a circuit that has many inputs and many outputs the output distribution of the circuit when fed as an input the uniform distributions over its inputs. So in other words, if we take a set of random coins and feed it to a circuit and see what it produces, the output distribution that it generates will associate with the circuit, and we'll say that's a sampleable distribution. The circuit is sampling from this distribution. So with these two definitions, we can now define our complete problem, which we also call statistical difference, which consists of the following problem. Instances to our problem will be pairs of distributions, pairs of sampleable distributions, given a circuit, C0 and C1, where yes instances are pairs of circuits that are somewhat far apart from each other, whereas no instances are pairs of distributions that are somewhat close together to from one another. So in other words, more specifically, yes instances consist of pairs of distributions that have statistical difference at least 2/3, whereas no instances consist of pairs of distributions that have statistical difference at most 1/3. And what we're able to show is that, in fact, this problem is complete for statistical zero knowledge. What this completeness theorem says is something quite remarkable. This completeness theorem shows that the assertions that are provable in statistical zero knowledge are exactly those that can be cast as comparing the statistical difference between two sampleable distributions. And in particular, it gives us a characterization of statistical zero knowledge that makes no reference to interaction or zero knowledge. And as a result, it provides us with a powerful tool for proving general theorems about statistical zero knowledge. We prove this completeness theorem through a 3-step approach. In the first step, we examine general properties of the simulator's output. And we try to identify certain properties of the simulator's output that allow us to distinguish between yes instances and no instances. In other words, we try to identify behaviors of the simulator that distinguish between the simulator's behavior on a yes instance and the simulator's behavior on a no instance. In the second step, we try to take these properties and actually embed them into our complete problem statistical difference. In other words, how to cast them as a statistical difference between two samplable distributions. These two steps together allow us to get a reduction from any problem in statistical zero knowledge to our complete problem statistical difference by means of the simulator. Finally, to complete the completeness proof, we simply exhibit a statistical zero knowledge proof for statistical difference, which shows the statistical difference itself is in SEK, completing the loop. Yes?
Is the notion of reduction that you use randomized polynomial time reduction, or what is the notion of reduction?
So we use a standard polynomial time CARP reduction, just instance-to-instance reductions. So let's take a look at the first step in greater detail. So again, in the first step, we're trying to look at the simulator, look at general properties of the simulator, and identify properties that distinguish between yes instances and no instances. The first step in our analysis will actually be a conceptual one. We'll think of the simulator's output not as simply producing some string that shows this kind of a transcript, but actually as being a virtual interaction between a virtual prover and a virtual verifier. Now, what do we know? We know that given a yes instance, the virtual prover makes the virtual verifier accept with high probability. This is again because for a yes instance we have a good simulation, which means that in particular the virtual prover should make the virtual verifier accept with high probability. On the other hand, we also know that the virtual verifier behaves just like the real verifier, since again we know that it is a good simulation for the case of a yes instance. What we're able to show is that in fact for a no instance, we can't have both of these two conditions holding simultaneously. Now, to see why that's the case, let's suppose that it wasn't true. Suppose that in fact for a no instance, both these two conditions held simultaneously on the simulator's output. Well, in that case, let's consider a cheating prover strategy that simply tries to mimic what the virtual prover does. Now, what do we know? We know that the virtual prover makes the virtual verifier accept with high probability. On the other hand, we know that the real verifier behaves just like the virtual verifier. So this means that this cheating prover that just mimics the virtual prover we'll be able to convince the real verifier to accept a no instance with high probability. This, of course, contradicts our basic definition of statistical zero knowledge proof, which shows that in fact this can't be the case. So we know now that for a yes instance, both these conditions hold, and yet for a no instance, at least one of these two conditions must fail to hold. Yes?
So do we know what the virtual prover and verifier are?
So the virtual prover and the virtual verifier are just sort of mental constructs that are looking at the simulator's output, and we're just interpreting the simulator's output as being the interaction between a virtual prover and a virtual verifier. So the virtual prover and the virtual verifier really just refer to the simulator's output. Okay. So this first condition is, of course, quite easy to deal with. We can decide whether the virtual prover makes a virtual verifier accept simply by looking at the simulator's output and deciding whether it actually does make whether the verifier really would have accepted that output or not. But of course, the second condition is much more nebulous. What does it mean for a virtual verifier to behave just like the real verifier? So our main challenge will be at how to quantify this notion of the virtual verifier behaving just like the real verifier. To do this, we are aided by a theorem due to Okamoto. What Okamoto showed is that in fact, it's possible to transform any statistical zero knowledge proof into what's called a public coin proof. In a public coin proof, the verifier simply sends random messages to the prover. The verifier simply takes a set of random coins, flips them, and sends them over to the prover. And the prover responds just as he would in a normal protocol. These kind of proofs are called public coin proofs. And so as a result, we can focus without loss of generality on these public coin proofs. So now let's re-examine the second condition, that the virtual verifier behaves just like the real verifier. Well, for a public coin proof, the real verifier behaves in a very simple manner. The real verifier simply flips random coins and sends them over to the prover. So for a public coin proof, we can actually quantify this notion of virtual verifier behaving just like the real verifier to simply mean that the virtual verifier's coins, the virtual verifier's messages, are A, nearly uniform, and B, nearly independent of the conversation history. And if we have these two conditions holding simultaneously, then the virtual verifier is behaving just like the real verifier. And finally, what allows us to complete the reduction is the observation that these two properties of the virtual verifier's coins being either nearly uniform or nearly independent of conversation history, these can be captured exactly by the statistical difference between two sampleable distributions. So with this argument, we've argued the reduction. We've shown that every problem in statistical zero knowledge does in fact reduce to our problem statistical difference. We still need to argue that statistical difference itself has a statistical zero knowledge proof. So again, just recalling, our complete problem consists of pairs of distributions that are either somewhat far apart or somewhat close together. And we have to now give a statistical zero knowledge proof for this problem. The first step in giving such a protocol is something which we call the polarization lemma. In the polarization lemma, we show that there exists an efficient transformation that transforms a pair of sampleable distributions to a new pair of distributions such that if the original pair are somewhat far apart, then in fact the new pair of distributions will be almost disjoint from one another. On the other hand, if the original pair of distributions were somewhat close together, then the new pair of distributions will in fact be almost identical to each other. And of course, what makes this lemma non-trivial is that in fact these two properties have to hold simultaneously. The transformation, without knowing which of these two cases it's in, has to be able to satisfy these properties. The key ingredients in proving this lemma are first a technique that allows us to increase the statistical difference between two distributions, in other words, make them more and more disjoint. And in fact, this can be done by something as simple as independent repetition. And then we use an alternative method to do the opposite, to take a pair of distributions and in fact make them closer and closer to each other. And finally, we prove this lemma through a careful balancing of these two methods. Once we have the polarization lemma, the protocol itself is actually quite simple. In the protocol, first both the prover and the verifier use the polarization lemma to compute these new pair of distributions, D0 and D1, that are either almost disjoint or almost identical to each other. And again, the prover is trying to convince the verifier that D0 and D1 are in fact almost disjoint. What the verifier then does is flips a random coin to choose one of the two distributions, either D0 or D1. It then takes a random sample from this chosen distribution and sends it over to the prover. The prover must then guess which distribution the sample came from. And it does so by simply choosing the one that it was more likely to have come from. And finally, the verifier accepts just if the prover has guessed correctly. If the prover's guess, in other words, is equal to the value of her random coin. And our claim is that this simple protocol is in fact a statistical zero knowledge proof for our problem. And to see why that's the case, first to see why it's convincing, we notice that if we have a no instance, if the two initial pair of distributions are actually somewhat close together, well, in that case, D0 and D1 will in fact be almost identical to one another. They'll have exponentially small statistical difference. In that case, the samples from one distribution are almost indistinguishable from samples from the other distribution, and therefore the prover won't be able to guess correctly with probability much better than a half. And so the verifier will catch the prover in a lie with probability pretty close to a half. On the other hand, if we have a yes instance, in that case D0 and D1 are almost disjoint from one another, and in that case the prover will be able to guess correctly almost all the time. And so in fact, the prover will almost always be able to convince the verifier to accept. So that's why this protocol is convincing. And in fact, zero knowledge comes almost for free in this protocol. And that's simply because in the case of a yes instance, again, when D0 and D1 are almost disjoint from one another, in that case, the prover almost always guesses correctly. And the only information the verifier gets from the prover is a single bit, just the prover's guess, either D0 or D1. And again, for the case of a yes instance, this guess is almost always correct. In other words, it's equal to the verifier's coin, which of course the verifier already knew to begin with. So this intuition shows that indeed this is a zero-knowledge proof, and this can be turned into a formal proof in a very straightforward manner. So we've now argued both sides of the completeness theorem. We've shown that every problem in statistical zero-knowledge reduces to our problem, and also that our problem has a statistical zero-knowledge proof, which allows us to complete the proof. Yeah?
How do you have to pick K in this construction? You have this parameter K.
Right.
And why do you have to pick it as big as you pick it?
Okay, so this parameter K is actually, can be specified to be anything you want. So it can just be specified to the lemma as an auxiliary input, and you can make this probability as small as you want. So in particular, that means that we can make these probabilities as close to this, we can make these two distributions as close to each other as we want, or as close to disjoint as we want. So in fact, we can pick K to be any security parameter you like. Any level of confidence you'd like to have, you can pick K accordingly, and that'll and push through the protocol with that particular choice of K. So it's really up to you. Whatever you want to choose K, whatever level of confidence you'd like to have, you can pick that. Yes?
So since C0 and C1 are defined by circuits,
Yes.
how does the growth of D0 and D0 and D1 would be described by larger circuits, right?
Yes.
So how does that dependence go?
So that it's simply polynomial in the size of the original circuits and this parameter K. So it can be it just grows in that manner. So with these two arguments, we've completed our completeness proof, and we can now move on to applications of our complete problem. So one very simple application is the existence of very simple protocols for statistical zero-knowledge proofs. So we know, we've argued that in fact every problem in statistical zero-knowledge reduces to our problem statistical difference. And know the statistical difference itself has this very simple two-round protocol that I just described. One that in fact only has one bit of prover to verifier communication. And again, because it is complete, this means that every problem in statistical zero-knowledge has such a protocol. So that's the first immediate consequence of our complete problem. We're also able, as I mentioned earlier, to simplify the proofs of nearly all known previous results. And just to give you a couple of examples, one result that I mentioned earlier was this proof that statistical zero-knowledge can't have NP-hard problems unless an analog of P equals NP holds. This result, in fact, follows with just a few lines once we have our completeness theorem. Another result that was previously known was that statistical zero-knowledge is closed under complementation. In other words, if a problem pi has a statistical zero-knowledge proof, then so does the complement of that problem. This result also follows in a very straightforward way from our completeness result. And in fact, we can give an explicit transformation that transforms our complete problem to its complement. And indeed, there are many other examples as well. But again, we're not just limited to proving results that we already knew. We can also prove several interesting new results. And just to give you one example, we're able to show that statistical zero-knowledge not only is closed under complementation, but in fact has much more powerful closure properties as well. The formal statement of our result is somewhat cumbersome, so let me instead give you an example. We know that graph isomorphism has a statistical zero-knowledge proof. But using our closure result, we can in fact show that the following statement has a statistical zero-knowledge proof. Given n different graphs, G1 up to Gn, I can prove to you in statistical zero-knowledge that exactly n over 2 of these graphs are isomorphic to each other. Now at the end of this proof, not only will you not know what the isomorphisms are between these various graphs, you won't even know which n over 2 of the graphs are involved in these isomorphisms. All of these results are made possible by our ability to focus on a single complete problem and prove general results through simply focusing on a single problem. So we can now move on to the second result, which deals with defending against cheating verifiers. So far in this talk, I've only talked about zero knowledge versus the honest verifier, where the verifier follows the protocol as specified. But of course, for cryptographic applications, one typically requires robustness against behavior that deviates from the protocol. And indeed, a natural question to ask is how much cheating can we actually tolerate on the part of the verifier if it tries to extract information from the prover? And what we're able to show is that, in fact, we can tolerate any amount of cheating. We give a transformation that shows how to transform a proof that is zero knowledge only for the honest verifier into one that is zero knowledge for any verifier, no matter how it deviates from the protocol in an effort to extract information from the prover. And again, this result requires no unproven assumptions. And it has several immediate consequences. The first consequence is, in fact, all these results that we've obtained about the honest verifier notion of statistical zero knowledge carry over to the more general notion as well of zero knowledge against arbitrary cheating verifiers. It also gives rise to an interesting design methodology. If we wanted to design a statistical zero knowledge proof for some particular problem, we could simply design an honest verifier proof and then use our transformation to generically transform it into one that's robust against arbitrary cheating verifiers. So before I tell you more about this result, let me tell you how we changed the definition to handle arbitrary verifiers. So we'll simply take the intuition that we started with for ordinary statistical zero knowledge and make it now hold for arbitrary cheating verifiers. So again, we'll simply require that when we have a true assertion, when X is a yes instance, now for every verifier, we should be able to simulate this particular verifier's view of its interaction with the prover. So again, since we can simulate the interaction of any verifier with the prover, we obtain our result. We indeed have that this protocol is zero knowledge for any verifier. And the formal, yes?
What does it mean for a verifier to be cheating? What are they not supposed to be allowed to do?
Okay, good. So I can give you an example based on the protocol that I showed you for our complete problem. So let's take a look at this protocol, right? Now, in this protocol, the honest verifier is simply supposed to flip a random coin to pick one of the two distributions and take a random sample from it and send it over to the prover. But a cheating verifier might instead look at the two circuits, D0 and D1, and decide, if I knew this particular string, if it was more likely to come from which circuit, that would give me a great advantage in figuring out the difference between these two circuits, for example. And a cheating verifier would be able to pick such a string, send it over to the prover, and the prover would tell it which one it was more likely to have come from. That is information that it could not have acquired on its own. So in particular, that's one example of the kinds of things that a cheating verifier can do. Okay, so again, formally, we simply now require that for every verifier, there exists a probabilistic polynomial time simulator such that when given a yes instance, the output distribution of the simulator is statistically almost identical now to this particular verifier's view of its interaction with the prover. There has been previous work in this area, but almost all of the work that was done earlier required unproven assumptions. So the results that were known to hold based on unproven assumptions due to Bellaria, Micali, and Ostrovsky, and culminating with the work of Okamoto, show that if one-way functions exist, in that case, we can transform an honest verifier statistical zero knowledge proof into almost any verifier statistical zero knowledge proof. Where here, the almost refers to the restriction that our cheating verifiers have to be polynomial time. And again, we require some unproven assumption to make this transformation hold. The only previous result that held with no unproven assumptions was a result that showed how to transform honest verifier statistical zero knowledge to any verifier statistical zero knowledge, but only for constant round public coin proofs. So these are only, again, public coin proofs where the verifier simply sends random coins to the prover, and only with a constant number of rounds. what we're able to show is that in fact we can extend this result to hold, again, without making any unproven assumptions, to hold for all public coin proofs. And in fact, this transformation extends to other types of zero knowledge as well, in particular what's called computational zero knowledge. Yes?
You just convinced me a few slides back that we never have to worry about anything except for two-round proofs. So
Okay.
Why should I not think of that anymore?
Good. So here we're restricting to public coin proofs. Now the two-round proof that I showed you was not a public coin proof. In that the verifier had to sample from some arbitrary, some unknown distribution, which wasn't just truly random coins. So it turns out that if we transform that protocol into a public coin proof, we actually require a polynomial number of rounds. So all currently known transformations require a large blow-up in the number of rounds in order to transform from a private coin proof to a public coin proof. Okay, so, and indeed, our result, which holds for all public coin proofs, extends to other types of zero knowledge as well. And again, this result suffices for proving what I claimed earlier, because again, public coin proofs are without loss of generality for statistical zero knowledge, and therefore our transformation indeed works for all statistical zero knowledge. So in the interest of time, I'll skip the details of this construction and summarize. So before our work on statistical zero knowledge, we had many interesting results were known about statistical zero knowledge, but our understanding of statistical zero knowledge was fragmented. We had several results, but not very well connected with each other. In our work, we're able to present a unified picture through two main results. In the first result, we were able to give a single problem that is complete for all statistical zero knowledge. And in particular, this allowed us to simplify and unify nearly all the previous work in the area, and also allowed us to obtain several interesting new results, answering many of the fundamental questions that were left open in the past. One drawback of this work is that it only dealt with honest verifier statistical zero knowledge proofs, which aren't so interesting cryptographically. To get around this problem, we give our second result, which was how to transform any proof that is zero knowledge only for the honest verifier into one that's zero knowledge for any verifier, which finally leaves us with a single coherent picture of statistical zero knowledge. And before I conclude, I'd like to mention that the work that I've presented here represents one of the two main directions of my research in cryptography, in particular trying to reach a deeper understanding of some of the fundamental notions within cryptography, in this case, statistical zero knowledge. The other main focus of my work is in trying to extend the theory of cryptography to deal with new challenges that haven't yet been addressed sufficiently in the work in fundamental cryptography. One area that I've worked in the context of zero knowledge is the problem of concurrency. So here we discussed a little bit about the problem when there's a single verifier that tries to cheat in an effort to extract information from the prover. But what if now we had many different verifiers that were all together orchestrating a concurrent, coordinated attack on the prover in an effort to extract information from it? That actually turned out to be a much more complicated and challenging situation to deal with, and that's been the focus of a number of papers that I've written along with some ongoing work. Another problem that comes up is the problem of key exposure. So typically in cryptography, in applications such as encryption or digital signatures, we typically require that all parties have some small secret key that we assume they keep hidden from all adversaries. But a problem that comes up often in practice is a problem of key exposure, where partially the key gets exposed to some adversary. What we're able to show is, in fact, a technique for taking any cryptographic scheme that's secure in the normal sense and extend it to a new cryptographic scheme that's secure even if almost all the bits of one secret key are revealed. These are just two examples of the other type of work that I do in cryptography. I also have several interests outside of cryptography, in particular in algorithms, learning theory, and the theory and application of error correcting codes. So thank you very much.